All right, so the next things we need to calculate are inner products of the function we care about, which is the completed Riemann zeta function times this Eisenstein series ZW times this holomorphic cusp form of weight k. Take the complex conjugate and stick this in so that it's weight 0. And this inner product with, say, this Moss form mu j. So remember that mu j, we're saying, has a Fourier expansion of the form sum n not equal 0 rho sub j of n times square root y k to the I rj 2 pi ny e nx. So we're just defining these rho j to make this true. And here, when we unfold, here we're going to unfold this. When we unfold the Eisenstein series, we get this integral. Y goes from 0 to infinity. X goes from 0 to 1 of pi to the minus w, gamma of w, zeta of 2w, and then this will just be a y to the w after unfolding. And then we have the Fourier expansion of this piece. So I'll write this as sum m goes from 1 to infinity of Fourier coefficient am conjugate, because we're conjugating, and then I'll stick this y to the k over 2 in right here, and then the e to the 2 pi I mz, well, I'll write that just as the x part and the y part separately. So the y part is e to the minus 2 pi my, and the x part, after taking this complex conjugate, is e of minus mx. And then we have our mu j, so I'm going to just take this Fourier expansion that we've assumed is what it is, and here, because we are taking this complex conjugate, I have to stick a complex conjugate here. Conjugating this does nothing, conjugating this does nothing. When you conjugate the k-Bessel function, you put a conjugate over this thing, so I'll turn that into minus irj, but then we also saw previously that you can do the change of variables in the definition of the Bessel function. T goes to 1 over t, and you can replace whatever's down here with minus whatever's down here. So this is actually invariant under complex conjugation. Of course, the argument here, 2 pi absolute value, and y also, I mean, it's real, so it's going to be invariant under complex conjugation. And then you have to have a minus here. And then we have our usual measure, dx dy over y squared. And here we're going to need that n is equal to minus m to get a non-zero integral in x. So what do we end up getting? We get a sum. M goes from 1 to infinity of, so the stuff that doesn't depend on x and y, we have our completed Riemann zeta function here. And we're going to have this 2 from right here. We're going to have an am conjugate, and then we're going to have a rho sub j minus m, right, because n has to be minus m conjugate. And then we have stuff that depends on y. So here it's going to be, I like writing the k-Bessel function first, so it's k irj 2 pi, and I'm just going to write m here because it's the absolute value of n, and n is minus m is positive. And then there's an e to the minus 2 pi my from this right here. And then we have our powers of y. So it's a y to the w plus k over 2 plus 1/2, and then I'm going to take a 1 from down here. So it's w plus k minus 1 over 2 dy over y. And now again, using that Gradstein and Rizek formula for the Mellin transform, we can write down what this is. So the whole thing is going to be sum m from 1 to infinity of 2 times pi to the minus w gamma of w zeta of 2w a m conjugate rho j minus m conjugate. And then here we have a 4 pi m to the w plus k minus 1 over 2 in the denominator, numerator of square root pi, and then we have gamma of w plus k minus 1 over 2 plus I rj times gamma of the same thing but with a minus IRJ. And then here in the denominator we'll have a gamma of w plus k minus 1 over 2 plus 1/2. And again, we're quite lucky that there's no hypergeometric function because this 2 pi m and this 2 pi m, these are equal, so we're just evaluating a hypergeometric function at 1, or at 0, sorry. And we can clean this up a little bit by just taking out all this stuff that doesn't depend on m. Again, we're quite lucky that there's so much stuff that doesn't depend on m, and we get that this is 2 square root pi times pi to the minus w gamma of w zeta of 2w over 4 pi to the w plus k minus 1 over 2 times our gamma functions. So gamma of w plus k minus 1 over 2 plus I rj times gamma of w plus k minus 1 over 2 minus IRJ over gamma of w plus k minus 1 over 2 plus 1/2, and then we get this Dirichlet series, sum m from 1 to infinity of am times rho j minus m, both conjugated, and in the denominator we have an m to the w plus k minus 1 over 2. Okay, so that was a little bit messier than the previous ones. I hope I didn't make any mistakes. And next up will be this inner product, but with an Eisenstein series instead.